Welcome back to ECE 441A, 541A. It's a warm morning this morning. Inside joke for those that are in class. It won't be inside for very long. You'll start to see damage of the event that occurred earlier. I apologize, so if you want to move back 2 or 3 rows, that's fine with me. It won't offend me too much. Today is the day before our first exam, and homework number 2 is due today. There is practice material on the website for exam number 1, and some of you are still trying to find team assignments. That's okay, it's a little late, but please try to find a team that you can work with. One announcement that you might be interested in is we will not be in class on Monday. So I have commitments besides just exercising that I have to attend to on that Monday. But watch for the material, video, and notes on D2L. Hopefully those will be posted at that point. What I want to do today is talk about the process for exam number 1. Hopefully we will have enough chairs, but please be ready to move around and shuffle on Friday. And today what I want to do is review how to develop these equations for the second order system. Somebody asked if I was reviewing today, so I will say this is a review of the system identification relationships for a second order system. Here's the process for exam number 1. Those quote marks mean inches. If you're not familiar with that, those are 8.5 by 11 inches. That's a standard page size in the United States, not too many other places, but you can have that covered front and back for 1 page of notes. I've placed table 2.3, a photocopy of that, on the website. That's under the exam number 1 material. I think it's at the bottom of that module. You can bring that in for being able to go back and forth in the time domain and the frequency domain. You can bring a calculator, and I'm not going to inspect your calculator. It can be whatever calculator you want. Bring something to write with, but everything else is not allowed. No book, no notes other than your 1 sheet, no cell phones, no computer, no buddy. So that's where we're at with exam number 1. Are there any questions? There's plenty of practice exams, I believe, on D2L that you should be able to see a little bit of a review from that. Questions? Round 2. Thought I exercised earlier. Not now. Sorry. Here's our system in the lab. It's an underdamped system which consists of a spring, a dash pot, and a mass, and an applied force that we are indicating has a scaling constant associated with it, and that's this gamma. This gamma is a constant, and we need to identify that relative to the electrical signal that we apply to the system to make it move, and then there's mechanical. All of that is lumped into this gamma. But you should be very comfortable with this second order dynamic equation, mx double dot plus bx prime plus kx equal gamma u. You should be able to put that into a block diagram if you were given that equation. That could be a review for exam number 1. If you Laplace transform that time domain differential equation, you will now find, or can find, the transfer function, which is the ratio of the output, which is the position, over the input, u. And in the lab, that input is actually specifying a number of counts. You tell it to go 2,000 counts, where 1,604.1 counts equals a centimeter. So you're basically telling it to go to a particular position. Here's the second order transfer function written in a couple of different ways, sort of two standard ways. The first way is in explicitly identifying the real part and the imaginary part of the poles. Minus sigma is the real part, omega sub d is the damped frequency of oscillation. That's the imaginary component. The other representation is in terms of natural frequency, omega sub n, which is the hypotenuse. That's the length of the pole away from the origin. And zeta, which is our damping ratio. And that's related really to this ratio of real part to the hypotenuse. But it's really, where is this pole in terms of its real part and imaginary parts, and omega sub n is the radial distance away from the origin. Sigma is just zeta omega sub n, and the Pythagorean theorem allows us to say that omega sub n squared, the hypotenuse squared, is the real part squared plus the imaginary part squared. And I'm hoping that when you see that transfer function, you start to picture this S-plane plot of poles and the different variables and how they're related to those pole locations. Or in this case, it's the one pole in the upper part of the S-plane, but it has a cousin or its conjugate downstairs in the third quadrant. But we usually just look at the second quadrant and relate these different values, minus sigma, omega sub d. We can sketch the hypotenuse, and then we can measure that angle theta, either analytically or with a protractor. But we can identify that angle theta. And in some of these highlighted areas near that figure, you can see the relationship between the damped frequency of oscillation, which depends on this factor of square root of 1 minus zeta squared, relative to the hypotenuse, or the natural frequency, omega sub n. Likewise, the cosine of theta is just the adjacent over hypotenuse, but the adjacent in terms of the damping ratio is zeta omega sub n. The omega sub n's cancel, and we see that the cosine of theta is that zeta. Or if you wanted to find theta, if somebody gave you a zeta, and somebody might at some point, they may give you the percent overshoot, which for a second order system, you'll be able to, after today's class, translate that into a damping ratio. And once you have the damping ratio, zeta, you can then find that angle theta. And then you know the relative amount of real part and imaginary part for that complex pole. Here's our step response configuration. G is the transfer function that we're interested in identifying, and our input, R of S, let's say, is a constant, and in the lab that might be 2,000, that capital A. For counts, it's 2,000 counts. If we now incorporate that input structure, A over S, together with the structure, the assumed structure of our, and I may call this a pure two-pole system. Pure meaning I don't have any zeros. It's only finite poles. So if I say a pure two-pole system, that means that you don't have to worry about a finite zero in the numerator. You now have a constant in the numerator. And that gives us then capital A alpha upstairs and this multiplied out quadratic and the S due to the step input from our constant input. Now what I want to do is actually convert that into something that looks more or has better properties or is easier to inverse Laplace transform or easier to deal with, and for that reason I'm simply going to multiply by 1. I can always hit something with 1 in terms of a scaling, and it's not going to modify that value. If I hit 3 with 1, it's still 3. Here I'm simply using a nice 1, which is omega sub n squared over omega sub n squared. I can put one of those omega sub n squares in the numerator. I can put the one that was in the denominator of the numerator, and now I have a scaling fraction, or some scaling value, capital A alpha over omega sub n squared, scaling this more, or this nicer transfer function involving omega sub n squared in the numerator. And that's going to be what we focus on during the derivation or the discussion today, is this scaled version of the actual output y, and we're going to call that y bar. But I hope that it's fairly easy to see what happens when we apply the final value theorem to that y bar. Y bar in the limit is the limit as s goes to 0 of s times y bar of s, and now that s cancels that s, and we now can look at the limiting value. I hope my computer is waterproof. Sorry. And we now have a ratio of omega sub n squared over omega sub n squared, which is 1. And that gives us a nice value for this y bar. In the limit, it's going to have a value of 1. One more scroll, and then we'll slow down and start to derive some of these relationships. Really, we want to now find the natural frequency, omega sub n, the damping ratio, zeta, and the scaling in our transfer function, alpha. And I'm just trying to illustrate the shape. This is maybe a poor sketch, but red and blue should be in sync in terms of where they're going high and where they're going low. It's just that one is a scaled version of the other, and that's all related to this relationship. Y is now capital A alpha over omega sub n squared, different from y bar. But we just derived where we know y bar is going in the steady state. It's going to 1. And we will use that to help us in some of this discussion, but I hope you can see, if my sketch was drawn more accurately, that the time to peak for y bar and y are the same. They're just scaled versions of each other. They're going to be at maximums at the same time. Y bar will peak at the same time y does, and we want to, in the lab, you're going to be getting this red curve. But now if you can measure the time that it peaks and the value of that when it peaks, which I'm calling y of t sub p, and if you measure A1 where you finally settle, then you'll be able to get the percent overshoot. And that percent overshoot is something that we will want to have for finding zeta, and we will also use it to find omega sub n and alpha in sort of a sequential pattern. Yes? A sub 1 is the final value that you're going to get in the lab, which if we now say system, go to 2,000 counts, maybe A1 will go to 2,400 counts. So you'll measure your final value. Where does the system actually settle? And you'll see that maybe it's 2,400, or maybe it's 1,850. Is that what you were asking? Yes, so this A1 we will relate to this A, but they're not the same. So this A in the expression for Y is the 2,000, what we push it. This is where we command it. That's what we would like. Ideally, we would like A1 to go right to where A was, but in reality, it's probably not. So A1 will be different from A, and we'll find that as we go through the development. But now let's find a way to relate this peak time, T sub P, to the damped frequency of oscillation, omega sub D. And to get us started, what I want to remind us of, well, we are going to be looking for the derivative. How do we find, I just gave it away, how do we find maximums, derivatives? So we are anticipating differentiating y bar in order to find where is that maximum occurring. That's what I'm saying now. Anticipating needing the derivative of y bar of t. What do we actually have available to us? We now have a Laplace transformed version of y bar. We have capital Y bar of S. And how would we differentiate that in the frequency domain? We would multiply by S, and it's convenient because we have one S that's just hanging there in the bottom to be canceled, isn't it? So we are going to be wanting to find the derivative of the time domain, little y bar of t, and we're going to do it indirectly by differentiating in the frequency domain and then inverse Laplace transform. Meaning we can look at S y bar. And that's S times what we started with, which was this omega sub n squared over S times S plus sigma squared plus omega sub d squared. And those s's cancel. And we now have omega sub n squared over S plus sigma squared plus omega sub d squared. Does that look like something that you would find in Laplace transform tables? Sort of, except is the numerator what we want it to be? We want it to be just omega sub d, no squaring, no natural frequency. We want the numerator to only be the damped frequency of oscillation, omega sub d. Well, we can put that in there, can't we? Again, by multiplying by 1. Meaning, let's now introduce an omega sub d. We want it in there, let's put it in there. But what that now says is that we are going to be scaling this. Eventually, this is going to give us an omega sub n squared over omega sub d, scaling what we want. Now we have an omega sub d over S plus sigma squared plus omega sub d squared. And what's in black is what we feel more comfortable finding in a Laplace transform table, and the red is just a scaling factor. And this is actually the S y bar. Meaning, if we want to find the derivative in the time domain of y bar of t, then that's going to actually be the inverse Laplace transform of S y bar of S. Which is what? Can you inverse Laplace transform that black bracketed expression? What is that expression in the black brackets in the time domain? Is it a sine, or it's an exponentially damped sinusoid? Is it a cosine or a sine? It's a sine. The cosine has the linear factor S plus sigma. We just have a constant, and it's actually the constant we want. We now know that we have an expression for the time derivative of our time domain y, little y bar of t. Is it clear where that came from? The exponentially damped sine wave is just coming from the inverse Laplace transform of the bracketed term up above, and the term in parentheses is a scalar. It just follows down, or it just comes down. It's a scaling value. We now know then that we have y bar prime of t equaling omega sub n squared over omega sub d e to the minus sigma t sine omega sub dt. And what are we really after? We were looking for the maximum, and how do we find the maximum from the derivative? We set it to 0. And we don't want it to be the trivial case at the origin. We want it to be 0 after the first t equals 0 length of time. So we don't want to just set e to the minus sigma t. Is that going to be a 0? No, it's not going to experience any highs and lows, is it? So now we don't need to really worry about that. We just need to worry about that piece and what it does in terms of when does this go to 0. We're saying we want y prime of t to equal 0 the first time after the trivial case, which would be t equals 0. When is sine of omega sub dt equal to 0? That's the only thing that we're really looking to go through maxes and mins. The e to the minus sigma t exponentially goes. It doesn't have maxes and mins. It doesn't oscillate. Meaning we're looking for when this happens. What do we need the argument to be in order for the sign of that argument to be 0? Okay, when omega sub d, when the argument is equal to pi, right? When it's pi over 2, it's at a max. And at 0, it's minimum, but we want it after that, so the first time after 0 that experiences a 0 is at pi. So now we've concluded that we now know that omega sub dt needs to be pi the first time after 0 in order to experience a maximum. Or this now gives us our expression for the time when we peak. It's the value of t that satisfies that equation. Our peak time, which we'll call little t sub p, is now pi over omega sub d. And that's one of our key expressions. If you now looked at, in the lab, your transient behavior, what are you going to identify? The peak time or omega sub d? If you get this measured data, this red curve, what can you experimentally find? The peak time. So now we really need to just rewrite that equation in terms of omega sub d equals something in terms of time peak. Meaning you can now use that same relationship to say that the time to peak can provide, and that's what one of the parameters we were trying to identify, is this damped frequency of oscillation, omega sub d. Or omega sub d is now pi over time to peak. And another reason for liking pi. Pi now gives us our damped frequency of oscillation. Question?
So, using once I know to get the equations right, a function of sine, but then talking about maximum derivative of 0.
So now what we were doing is we were actually doing the inverse Laplace transform to obtain the derivative. So you were getting a little bit ahead of us in terms of what we were doing, but here we were directly identifying the derivative of our frequency domain expression, and inverse Laplace transforming immediately gives us a sign. So we don't have to worry about differentiating sign, we just need to know when is the sign going to first be 0. Does that help? There's one of our parameters. There's omega sub d in our transfer function. Now what we want to do is find some more of those parameters, and the next one that we will find is from our response, we can find the percent overshoot. We want to find the percent overshoot, which we will typically abbreviate PO, and we want to relate that to our damping ratio, because that's another one of the parameters that we want to find in our second order transfer function. We want to find the relationship now between the percent overshoot and our damping ratio. Let's return to our picture. Here's time, and this is the time domain. Let's say that we now have this plot of y bar. And what did we already determine this is? We created y bar to give us a nice behavior. This was actually equal to 1 in the steady state, wasn't it? And we can now identify when this peaks. There's now T sub P. This is y bar of T sub P, or I might just call it y sub bar of P, to be the peak of y bar, just to minimize notation. So all we're saying is that the peak of y bar of T occurs at time t equal T sub P, and we already know what T sub P is. T sub P we just found in step 1, that's pi over omega sub d, and we may need to use that in our formula. Now, what we want is, it would be nice if we had an expression for y bar of t. And y bar of t we can show, or it can be shown, or you can find it in the Laplace transform tables. Y bar of t was this, where was it? Right there. That's y bar of t, this omega sub n squared over this quadratic standard form and an s in the denominator. So this is a step response behavior of a underdamped second order system with the appropriate numerator identified, omega sub n squared. You can actually find that in the Laplace transform tables. It may not look quite like this because I'm using some of our introduced notation, but it's 1 minus 1 over beta e to the minus sigma t. That shouldn't surprise you. That's the exponential decay. Sine, what do you think the frequency of that sine wave is going to be? Omega sub d, the natural, or the damped frequency of oscillation, and we may then have some offset. Ooh, let me call this a theta bar. Actually, I think it is the theta that we want, so let me just leave it there. So there it is, and you can find this either in the table. It's, I think, the second one from the bottom. It's not the bottom one, it's the next one up in Laplace transform tables, table 2.3. Or I derive it in the notes to lab number 1. So you could see this. I know that you all enjoy watching or reading those derivations. So this is note 1 in the demo 1 notes, where in this expression for y bar, beta is 1 minus, or the square root of 1 minus zeta squared, and theta is the inverse cosine of zeta. And now let's plug in what we know. We know t. We want to evaluate this at the peak time, t sub p. We now want to find what y bar of t sub p looks like on the right-hand side. Can it be cleaned up, or can it be simplified? We can measure what y bar at the peak time is from the physical data. We can just go and look. Oh, that's 2,850 counts. Don't use that in lab 1. That's probably not where it is, but you get the idea. It's some value of counts. We now know then that y bar at the peak time is 1 minus 1 over beta e to the minus sigma time to peak, which is pi over omega sub d, sine omega sub d times t, but t is the peak time, which is pi over omega sub d plus theta. And this is sort of begging us to look at in pieces. It usually helps to cut things up into pieces instead of maybe always looking at the whole. In this case, let's look at that piece. We'll call that piece number 1, and we'll call that piece number 2. What can we see in piece number 1? We have e to the minus sigma pi over omega sub d, where this is simply the parameterized version of the peak time in terms of our damped frequency. But we can now play with that a little bit more. How did we define sigma in terms of the natural frequency? It was zeta omega sub n, wasn't it? So we now have zeta omega sub n, that's sigma, and in parentheses we have pi upstairs, and omega sub d in terms of omega sub n. It's a scaled version of the natural frequency, omega sub n times the square root of 1 minus zeta squared. So this cleans up nicely, unlike, never mind. So this is now equal to e to the minus zeta pi over square root of 1 minus zeta squared. And that's going to be important. Now it's just that exponential is really just a function of one unknown value, zeta. We know pi. That's piece number 1. Let's look at piece number 2, which is this sine. And that one should be just screaming at us to go back and apply our trigonometric identities to it. It's the sine of the sum of two angles, where one of those angles is pi. And you already told me what the sine of pi is. All right? That's 0, so that's going to clean up nicely also. Let's now look at the second part. We have the sine of pi plus theta. That is the sine of pi times so it's now this changing, it's sine and cosine, and now what's my SIG in between the two terms? Positive or negative? Do you remember? I excuse you for not having this memorized. I just remember in high school, the trig teacher, she made up songs, and it was sine, 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 and I'm going, what? So I had, who knows if I remember any of these trigonometric identities, but now we have the sine, or let's say cosine of pi times the sine of theta. And this guy is 0, and this one is -1, so that the expression sine of pi plus theta is actually minus sine of theta, but we've described that in terms of beta before. Boy, bringing all my old teachers in, now my penmanship teachers would be frustrated. My trig teacher's already mad at me for making fun of her songs. All right. Now what? Let's put these pieces together. We now have the y bar of the peak time. That's 1 minus 1 over beta e to the minus zeta pi over square root of 1 minus zeta squared times sine of pi plus theta, but we reduce that to minus beta, which allows us now to clean up the betas and to move this sign over here to where now it's going to be a positive. So now sine of pi plus theta, we've reduced to the minus beta, and that was the second piece of our expression. We have 1 minus 1 over beta, the first term, times the second term. The second term is just minus beta. The first term is the e to the minus zeta pi square root of 1 minus zeta squared. So you can look at that a little bit later. I'm trying to run today, so in many different ways. We now have y bar of time to peak. We've now changed or simplified to 1 plus e to the minus zeta pi over square root of 1 minus zeta squared. And I'm going to call that this y bar of p. That's what we found. We've now found an expression. Maybe it doesn't look that much cleaner, but it's a lot cleaner than having a sign with 2 arguments, etc., and an exponent. What do we also know about y bar of final value? If we applied again, this, I'm just redoing this. We've already done this, and you probably remember what this is, right? This went to went to 1. By canceling those two and letting s go to 0, this now went to 1. Which means that if we look at this response again, we have this value. This is y final value bar, which is 1. And we know what this guy is. This point was y bar sub p. And if I ask you to compute the percent overshoot based on this picture, what would that be? Or in general, what's the general formula for the percent overshoot? Maybe I won't, let me not do this just yet so that you realize that you can use this percent overshoot formula in general. If I wanted to find the percent overshoot, what would it be? Have you done this before? It's the max minus the final over the final times 100%. That's the percent overshoot. The percent overshoot is now the peak, or the max, minus the final value over the final value. So there's our percent. It's the fraction over the whole. And this is now times 100%. This is the general formula meaning this was not based on y final value being 1. That's what we're going to end up with, but in general, if the y final value was 2400 counts and y peak was 3000, you would do 3000 minus 2400 over 2400, and that gives you your percent overshoot. So we now know, or we can use y bar is equal to 1 plus e to the minus zeta pi over the square root of 1 minus zeta squared. And we can now write down our percent overshoot using that. That's now 1 plus that minus what? 1 divided by 1 times 100%. So in our case, the percent overshoot is 100 times e to the minus zeta pi over the square root of 1 minus zeta squared. That's now our relationship between the percent overshoot and the damping ratio. And in the lab, you can measure the percent overshoot. You can find what the peak value was, what its final value was. You can compute using this formula the percent overshoot, and now you have that equal to some expression in terms of the damping ratio. But now you can immediately solve this for zeta. Maybe you intuitively see that. We can solve this for our damping ratio. And I'm not going to do that. I'm going to again send you where? To the demo 1 notes. So see note 3 in the notes, but you can now start looking at taking the natural, dividing by 100, take the natural log, and doing some algebra to find zeta. And the formula then ends up being zeta is equal to the natural log squared of percent overshoot over 100. Let's say that you had a 10% overshoot. PO would be 10. It wouldn't be 0.1. It's 10 divided by 100, so it's the net is 0.1, but PO here is the actual percent. Is that clear? So if you have a percent overshoot of 25, PO is 25. Then we have pi squared plus the natural log squared of PO over 100. And here's what you don't want to forget, and take the square root of that. And you can derive that from the previous formula. But now, given percent overshoot, which you can calculate, you can now find your damping ratio zeta. And we have one more piece to worry about. Now we need to find the relationship. We really haven't used anything relative to the final value and the applied input A. So let's find the gain constant in our transfer function, alpha, and the final value relationship. First, you guys are going to be experts at using the final value theorem. Now, let's use the final value theorem. to obtain alpha, where y of s, and now this is not y bar. Now I've jumped back to the full expression. This is now y of s. That was alpha over s plus sigma squared plus omega sub d squared. That was our assumed structure for our pure second order system, scaled by or applying a constant input, where the constant is a. So I'm not trying to bar this. This is y sub final value. This is the full output. Y is the limit as s goes to 0 of s y of s. And what does that equal? This s is going to cancel the s on the far right, and we will we let s go to 0. We now have a alpha over sigma squared plus omega sub d squared. And what were we calling y final value? That was the a sub 1. So that now we have a relationship for alpha. We can solve that expression for alpha, and we have a1. And what is this, or what's another way to write that expression? Do you see Pythagorean? This is a squared plus b squared equals c squared, where our c squared is the hypotenuse, and that's the natural frequency squared. This is omega sub n squared. So if we solve that for alpha, we have a1 times omega sub n squared over a. And all of that was obtained experimentally, meaning now we have our transfer function of a pure second order system, that's alpha, s squared plus 2 zeta omega sub n s plus omega sub n squared. Well, maybe we didn't find omega sub n explicitly, but we know how it is related to the damping ratio and our damped frequency. We know that omega sub d is omega sub n square root of 1 minus zeta squared. So if we know zeta, and how do we find zeta? That's from the percent overshoot. And what was our omega sub d? We found that from the peak time. So this is pi over time to peak over square root of 1 minus zeta squared. And maybe this should be our third cheer. What's our third cheer? Zeta is equal to, oh, this is too long of a cheer, but it's ln squared of PO over 100 over pi squared. Pi squared's a nice cheer. How much is that in round terms? 10. So pi squared is 10. If you need to make change or do something quickly and somebody says pi squared, just substitute 10. Oh, the homework you can hand in now. You can hand in my mailbox, or you can hand in on the Dropbox. Is there a Dropbox for homework too? Okay. So you're good to go for the exam after you study.